Dear ladies and gentlemen, I prepared first of the examples is pre-tangent pre-stressed beam. I wrote a very short tutorial, or better said handout for the presentation. In fact, I lecture at the university pre-stressed concrete, I used the example which I give to the students, but I think it can be used also as a general introductory example for the use of IDEA StatiCa prestressing. You can see the file which we will upload to our web, including the recording of this webinar. And as you can see, we have the design pre-tangent pre-stressed beam according to EN code. This one is not correct according to EN code. The span of the beam is 15 meters, and we have also other data given in the specification, which I will show later. I will not be going through these handout sheets. I will switch directly to the program, and I will show you how to input such beam. So I start new task, new project, and we have a wizard which can help you to input the geometry and some loads of the structure. So we are going to analyze prefabricated concrete beam, and the concrete will be pre-stressed, and there is an option of subsequent post-tangent which we will not use at the moment. We will have a single span beam, and here we have beam alignment and support positions. Once we fill in the data, we can press the button next, and we can see that the program asks about if the beam is straight or if it's curved in a plane or in elevation. What is the length of the beam? As we have 15 meter span, I assume overhangs at the ends of half meter, so it will be 16 meters together. We will want to use the standard EN code. We can also use some national annexes, but I will keep standard today. Our design working life is 100 years, and even if originally the beam was bridge, I will skip it now so that I make the example very simple. You have to input some cross-section. Today we will use this type of I shape with haunches, and you can adapt the data. Here the dimensions 350, depth will be 900, this is okay, 30 and 190. So that was the cross-section which I would like to analyze. Concrete grade is 50-60. Then we have to decide if we want to generate the cell weight of the beam according to cross-section automatically, permanent load, and some variable load. This is substitute variable load. I do not want to use these features of critical patterns, and I can go to the next table, and this is these are construction stages. These construction stages I decided to also to make very simple, only casting, pre-stressing. I will skip storage yard and transport for the time being, and final supports. I start with 28 days, and I will come back to that during the presentation. Final supports I assume at 60 days, superimpose the load at 120, and this is end of the design working life. You can also change the cantilevers at the end of the beam, but as I tested the example before the presentation, I have all the data already finished, already specified. So I can finish it, and now the program generates basic data. You can see that we have a beam with the cross-section. We have some standard data of the project. You can also see the cross-section here, materials, members, and other parts which we will come to these members and haunches later. So as I said, the program generated not only geometry but also loads and combinations. You can see now that we have cell weight, some dead load G. The number in the bracket means that the load is applied in second construction stage, prestressing, and some live load or substitute live load. Program generated load groups, variable and permanent, and we can just correct one data. That's the additional dead load, superimposed dead load, applied in the construction stage 5, which is, you can see the tooltip final supports, and that was -1, and actually this load was the load between in the joint between the prefabricated beams along the length of the beams. As I mentioned, I can add any point load, point moments, all these types of loads, also user-defined loads using the table copied from Excel, for example. This is very useful feature for the import of the forces calculated in some other software, or just the forces which you consider useful for the analysis. Program generated a combination. You can see fundamental, characteristic, and frequent and quasi-permanent combinations. All of these combinations are code combinations. That's why we see the combinations here. There are coefficients 1, but it just means that the load cases are present in the combination, and the program will generate the factors according to the code. So I will explain the structure of the combinations later. I will just change here intentionally the combination to 6.10. So it will be generated according to different formula. Now we can go to construction stages. I will skip setting. You might have noticed that I go through navigator from the top to the bottom. So if you don't really know what step should be next, and you can go down in the navigator. Here we can see the construction stages. Casting, the beam is green. Transfer of prestressing, we skipped storage yard. The transport, we can just check on this checkbox to get storage yard, final support, superimpose dead load. If we switch into load history here, you can see a graphical tooltip. Then you will see that principle of how we combine the loads. For example, the stage final support, which I have mentioned, is the stage here in 60 days. And at that time, the program applied R5, which is rheological load case, in which we store the effects from stage 2 to stage 5. You can see here that the load cases are R5 or G5, and also this G5, which was this additional superimposed dead load. So in these load cases, we store the increments, and if you sum all these load cases, you get the total value, which is the result of the combination, and it shows you a total structural response of the structure on loads applied in individual construction stages. This is the principle. Now we can go back to load cases just to explain why we didn't show this rheological load cases. You can press it on, and you see that we have also R, G, R, G for each construction stage. You don't want to see those automatically generated load cases, you can switch it off. You can also explain better now the combinations, so that I will edit it. And for example, this fundamental combination, I have only cell weight, one rheological load case, one G, and pre-tensioning. But if you go to final supports or superimposed dead load, or even to end of design working lives, you see that we have more load cases combined in this combination. One of them is this variable load. So the program generates these necessary combinations for you. Of course, you can add user-defined combination here with no problems. As you can see, this is quite useful because you do not need to learn the logic of the program. The program does not require it, especially as concerning construction stages and time-dependent analysis. The program generates these load cases, combinations, and model automatically based on the data you know, and then based on the data you input via tables. Now we can go to tendon design, and in fact the program will start a separate module in which we can input both pre-tangent and post-tangent tendons. Now we see the module. Again, we can see this structure response in time. We can also see not editable tables, what load cases and combinations are available in these stages, and we can go further in this navigator to design members and see the design members. First of all, I would like to show that we can see plane XY and XZ. It is, you see here, uncoiled view, which means that if we have a 3D structure, then it is uncoiled into 2D, and you simply work in 2D. You can switch off on these projections, and you can also make it scaled in vertical direction. Here now we have 1:1 scale, but if we want to scale it like this, then we can switch it off, and we have really beam in which you can edit the tendon and with no problems. So when we are happy with this, we can go to tendons, and I will use the possibility to input the tendon, pre-tension tendon inline. Here in the data window, you can see our predefined pre-stressing load case. The program selected first tendon on the list. My tendon will be Y860, this one. And I can go to the definition of the geometry. I know that either from some preliminary calculation or from my experience that I will have 5 strands. Or I can simply check it, and in several minutes I can check if it is correct or not. And also I define this data from vertex 6, which is 75 and 63, and here again minus 75 and 63. Sorry, 63. And you can see the tendons here, but also we can switch into cross-section here. Here we can see only one group of the tendons, and here we see all groups, which we still don't have. We will add one pre-tangent in line, and the number of strands will be again 2, but the geometry will be different. Here I will have again 75, 113 minus 75, and 113. And now it's okay. You can see this group. As we need to reduce the pre-stressing force at the beginning and at the end of the beam, we define blanketed length in which we have debonded strength 3 meters. So now you see that the tendons or strands are debonded in position 0 here. And if we go back to this, I can show we go to 3 meters, then it disappeared, so these debonding tubes disappeared. So that's it. We can go back to tendon tab sheet, and we see that we have 2 tendons. The program took the same material by default. What we don't have nice is initial stress, because this low stress was selected for previous type of tendon or strand. So I select both using shift, and I edit it here in this selected tendons, and I want to have higher stress. By the way, you can see now that we have all the tendon checks satisfactory. But if I go to 148, this high stress, it is bigger than the maximum, as program gives you the 1476. Then we see the tendon stress check is not satisfactory. But I will explain it later, or I will improve it later. Now we can go through this to see also force design. For pre-tangent beam, we should probably show Fx normal force and also My. We can of course show also the other components also acting in plane XY, but for this type of beam it is not necessary. Even this Fz is 0, so those are equivalent forces. And we can go to short-term losses. We see the table, summary table with checks which are not satisfactory at the moment. And here we have also the distribution along the length. Again, the check is not satisfactory. So what to do with this is that we have to check, change the parameter in the code. The code is in the parameter, we can filter it, of course. We have filters here, but I know that it is in chapter 5, and it is parameter K2. You see 51021, and we can improve it, increase it to 95%, which means that based on the Eurocode, that you can do it in the case that you measure the stresses in the factory with certain precision. So in that case, we can go to higher level of the stress, and you make your design more economic. Now we see that the check is okay. By the way, here I can see also info window, which I haven't mentioned yet. There is a status about what is imported from the beam. If there is some problem, there will be a cross instead of this Nike. The program tells us that the length of the beam is 16 meters, tendon length is 112, tendon mass together 132, and tendon mass per cubic meter is 28 kilograms of tendons per cubic meter. And also some other useful information in these windows about current tendon and so on. We can also go to design member results, but I would have to calculate. You see that it became red. We would have to run finite element analysis. Instead of that, I will exit this module, and I will go directly to the beam, and I will calculate time-dependent analysis. In fact, now the program calculates all the construction stages, including these sub-intervals necessary for proper analysis of creep, shrinkage, relaxation, and aging. The program calculated for all combinations which were generated before. Now we can go to, let's say, at least internal forces to see what are the internal forces. We select, let's say, ULS fundamental combinations, and you will see that we have such distribution of bending moments. You see bending moments for all construction stages and all ULS fundamental combinations. If we want to go to casting, then there is nothing, no force, because the concrete is fresh, and this is Selvey. Then we go to transfer of prestressing. Already we have some scatter of the moments, some differences. We go to final supports, then it is even bigger. Superimposed dead load, the moment increased here, and also end of design working life, you see different forces. You can see these forces in detail in the table here. Also, here you might notice that we have a factor 1.35 for cell weight, 1.35 for G2, which means this is the combination for ULS fundamental combination actually in construction stage 7 with index 9, which was identified as a critical for certain internal force. So you can search it here. When we have it and we are happy with the results, we can go to concrete design. First of all, we can mention that all these exposure classes and other data can be adapted. Also, checks can be selected which one we want. But we have to define reinforcement zones. For pre-tension beams, usually we have same reinforcement along the length. Possibly the shear reinforcement above the supports will be different, but for simplicity I don't mind at the moment. I simply want to check it in positions, and the first generated position was 8 meters, which was in the middle. As the program generates the sections according to the both geometry and the loads which are applied, I will use 7.99 just to avoid the case that in the middle the program generated very small point load caused by the tendon due to some effects which we cannot explain here, and now I avoid to generate two load cases, two positions, one just before and just after mid span. Second section would be at above the support. I am using the position 1.3 meters, which is at approximately the dimension D, which is you see 900 millimeters minus some concrete cover and centroid of the reinforcement. If we add 0.5, we approximately get 1.3, which is the section in which we should check it according to Eurocode. Once we have it, we can go to detailed analysis, run detailed check here, and the program runs again the module, which works also as a standalone program. You can see this IDEA StatiCa. If I open it, you can see we have, sorry, this is, I can switch into different language. We have English, Czech, Slovak, Dutch, German, Polish, and Italian language. And if I start it again, I have to start it again. Then it will be in English. And you will see that RCS is a standalone concrete, or in pre-stressing we have RCS, standalone reinforced concrete section program, which we also linked to this beam program, and the program generated the data for you. You can see two sections at 1.3 meters and at midspan, and also several extremes, extreme name, which are in 28 days, 60 days, 120 and 100 years. Also in each extreme you see one ultimate state combination, one serviceability, three serviceability, one characteristic, frequent and quasi permanent. So we can immediately start calculations, and the program ran these two sections in all these extremes. You see that in the first section above the support we have here unsatisfactory shear because there are no stirrups. In the second section we have unsatisfactory even the capacity, about 10% more, and as we check also the interaction of all internal forces, and the interaction calculation is based on the response of the section, and the response was not found because of not sufficient capacity. Then we put there 1000%, and it shows you that we did not find even the response. It means that we have to reinforce the structure. Before I do it, I can show you also these design members which were filled in this module, reinforced concrete sections. Then in design we have cross-section pre-stressing. I can show the construction stages. You cannot change it here because it was done, and I can show this on this axis. Yeah. If we have a composite section, then the cross-section changes, action stages, all these data imported from also internal forces from the beam. And now we go to reinforcement. And I use the template, and I will use 4 bars in the top 10 millimeters, 0 bars because I have already these strands, 1 bar in the middle just to reinforce the reinforcing cage, stirrups diameter 10 millimeters, 45 millimeters stirrups cover, and I will use stirrup distance 0.15 with the overlap 200 millimeters, and we will see. I will remove the dimensions. Now the program generated these stirrups, and we can go back to sections and we can calculate it all. Now we will see if it improved, and it seems that it did. The non-pre-stressed reinforcement improved the capacity by, let's say, 9%, which is not satisfactory. We have still 101, and here we have 107 for shear, which is still not satisfactory. I could change maybe more, put there more reinforcement or other things, but what I wanted to show intentionally was that I go to combinations, and I will change it from 610 to 610 AB. Of course, because we have to regenerate it, I have to recalculate it again. And I want to just to highlight the fact that according to Eurocode, if you use this combination 6.10, it is not as economic as 6.10 AB, which you will see in the program. Now we go to reinforcement, and again detailed. I run it again, and we see that it will be much better. This is at midspan, it is even satisfactory, and above, and we can also see which one was. You see, it is 94%. We can go through all the checks. I will and we see what is the capacity, and the biggest was 94.5, so it improved significantly. And this one, this shear still needs a little bit more. I would don't care about 0.7%, but if you really want to be strict, then we go to reinforcement. We select the reinforcement, and I will change from 150 to 140. And also the other stirrups, just because I want to have it nice in the report, stirrups in the same positions. Of course, if I wanted to have different distance of stirrups above the supports and midspan, I can do it by defining different zone of reinforcement. Now you see that we have it finished. All these calculations are done, and it is satisfactory. We can see brief report, each section only one row. Standard report, usually in pre-stressed concrete it is a little bit more than one page, in non-pre-stressed it is one page. Or detailed, which generates all the pictures and all data, tables, intermediate results. You can see the reinforcement, interaction diagram, torsion. There is no torsion here, but we calculate it as it was required by the user. Here also the distributions and other things. You can, this detailed report, you can set in here what tables you want, in which section, which checks you want, and in checks, for example, what explanation or non-conformity tables and other things you can set it. So I will cancel it now. It seems that we finished, let's say, in a quite reasonable time the design, but I admit that this design would not be acceptable in practice because of this data. Here we have 28 days transfer of pre-stressing, which is not acceptable in a prefab factory, and usually we can, or the user specifies the concrete strength at which we have to, or we can pre-stress it. So then we can put here 25 megapascals, and the program automatically calculated an equivalent age of the concrete. You can see also the tooltip here, what the program in fact calculates. This 1.9 is still quite long time. It should be less than 1 day, definitely, I know it, but it is equivalent time, okay, equivalent age in which the concrete would mature into the same level, to 30 or 25, now 25 megapascals, when we have 20 degrees Celsius. If we have some heating of concrete, of course it is less, but we work with equivalent time. Of course we lost the data, so then we have to recalculate it. By the way, if you input this 1.9 days as the age of the concrete, then it is not allowed by Eurocode unless you check also this really test the concrete strength. So the program would not allow this case if you do not specify this value. So we can go back to reinforcement, detailed, and if we calculate it now, we will see the results, and we already see that stress limitation is not satisfactory at the time of pre-stressing.